Ma'am,
Yes.
ma'am, can you once again explain the part case 2 of group of order 21?
Okay, group of order 21. Sure. Okay, so okay. So let's see. So the case 2 was what? So we are assuming here in 3 denotes the number of silo 3 subgroups. So we are assuming the there are 7 silo 3 subgroups. Okay. So there exist 7 silo 3 subgroups. So H say is silo. So what I have taken H. I have taken H to be a silo 7 subgroup, right? And there is only one silo 7 subgroup, so H will be normal subgroup of G because of that. And any group of order 7 is cyclic, so this H will be generated by this element X such that order of X is equal to 7, right? So order of X is equal to 7. So H has then what are the elements? 1 x, x square up to x to the power 6. These are the 7 elements of this group H, which is generated by X. It is a normal subgroup. Now, if I consider Yx, Y inverse, then this should belongs to H because H is a normal subgroup. That means Yx, Y inverse will be equal to one of these elements, x to the power r, where r is lying
Ma'am,
between
we are
1 to 6.
considering Y to be any element of G.
Yeah, so basically what I have considered here, so K is the let K be a silo 3 subgroup. Okay, and K is generated by Y. K is any silo 3 subgroup. There are 7 silo 3 subgroups, so I am choosing one of them. I am calling it K. Okay, and it is a silo 3 subgroup, so therefore its order is 3, and 3 is a prime number, therefore K will be a cyclic group, so therefore K will be generated by a single element that I am denoting by Y. Is this fine?
Okay, ma'am.
Okay. So now of course since H is normal, so Yx Y inverse will belongs to H. Okay. So Yx Y inverse I am writing as x to the power r, where r is lying between 1 and 6. Okay. So now I am examining what is y square x y to the power minus 2. So this is nothing but if I just apply this equality again and again, then I will be getting x to the power r square. So then y cube will be y cube x y to the power minus 3 will be x to the power r cube. But what is order of y? Order of y is equal to 3. Correct? So y cube is identity. That means this element is nothing but identity. Therefore, I am getting this equation which is satisfied by x. That means which power of r will appear here? Those powers which satisfies this condition. Is this clear?
Yes, ma'am.
Okay, so that means I need to satisfy this equation r cube is congruent to 1 mod 7. So now from this values of r, you can see that 1, 2 and 4, these are the only 3 values which is satisfied, which satisfies this equation. So I will have the choice r equal to 1, 2 and 4. Okay, so now I will consider these 3 cases. So first case I have assumed say r equal to 1. That means y inverse equal to x. Okay. So in this happening, y and x are commuting with each other. Okay. And you can check that it is enough that if x and y commutes with each other, then all the elements of the group will commute with each other. Will imply that G is an abelian
Ma'am,
group.
yes, I tried to prove that this is abelian, but I was only getting that the y's will commute with x. All y's we can show that these are in center, But how can we show that y is commuting with another um, element of order 3?
Yeah, so basically from here what you can say, so this group K, that is generated by X and Y, right? This group, sorry, this group G, if you see, now this group G, it will have either elements of order 3 or it will have elements of order 7, right?
Yes, ma'am.
So then there it will be generated by like a order 3 element or an order 7, generated by a order 3 element and an order 7 element. Okay, so any element of this group will be of the form x to the power something, y to the power something, where x is an order 3 element and y is an order 7, sorry, x is an order 7 element and y is an order 3 element. And this is true for any order 3 element.
Yes, ma'am.
Okay, so from there you can conclude that if this happening, then it will be nothing but all the elements will commute with each other, because all of the elements will be of the form x to the power I into y to the power j, or y to the power I into x to the power j form.
Okay, ma'am.
Okay, okay, so from there you can prove that G is abelian. If still you are not getting the arguments, maybe next time I will elaborately say how G is becoming abelian. Okay.
Okay, ma'am. Yes, ma'am.
Yeah. So you try for little, give little bit more effort in that direction. Okay. But if G is abelian, in that case, I know all the subgroups are normal subgroups, and in that case, G will be isomorphic with Z, the cyclic group of order 21. Because if G is abelian, then I will have this H and K, all the subgroups will be normal subgroups, and the previous, we will be in the previous case. Okay, so in that case, G will be a cyclic group. Okay, so now if I choose R equal to 2, then what I will be getting, Yx y inverse equal to x square. So now this is the relation. So my G is now generated by X and Y such that one element is of order 7, another element is of order 3, and they satisfy this equation. Okay, so basically if you see that this condition says that G will be generated by X and Y such that order of X is equal to 7, order of y is equal to 3, and you are having that y inverse equal to x. Now from here you try to conclude that G will be abelian. Is this fine? Now the more precise statement.
Yes, ma'am.
Okay, now I think you should be able to prove that G is abelian. Okay, fine. Now I'm assuming, suppose R is equal to 4. So if R equal to 4, then y inverse is equal to x to the power 4. But in the previous case, y inverse is equal to x square was there. So I'm trying to show that this case actually leading you to this case only. How? Because if this condition is satisfied, okay, then I can see that y square x y inverse will be equal to x to the power 4. But y square is again an element of order 3. And this relation is nothing but an order 7 element, how it is related with an order 3 element. So you are getting the same relation here and here. Here y square is also an element of order 3. So these two equations are basically the same equations.
Okay, ma'am.
Okay, so that's why we are again, this case is not a special or different case. This is again the same case that is here. Fine.
Yes, ma'am.
Okay, so now it's clear to everybody. Okay, so now let's start with today's lecture. So I have asked you, I think, to generalize for product of two primes. Have you tried? Yes or no?
Okay.
You tried? Did you get the general statement?
When Q are to prime number such that P is less than Q.
Okay.
There
And
are two
if
cases.
mm-hmm,
If P does not divide Q minus 1,
mm-hmm. So there are two cases. One case which is where it will divide, another case it will not divide. And
yes,
in these two cases, you will have two different types of groups, right?
yes,
Okay, so let me just explain it in the general thing once again. So let P and Q be distinct primes and I'm also assuming that Q is strictly less than P. And let G be a group of order PQ. Then it says that if Q does not divide P minus 1, in this case, G will be isomorphic with the cyclic group of order PQ. And if Q divides P minus 1, then and G is not cyclic, then G will be isomorphic with the group which is generated by two elements x and y such that order of x is equal to P, order of y is equal to Q, and I have this relation that y inverse is equal to x to the power s, where I am having that s is not congruent to 1 mod P and s to the power Q is congruent to 1 mod P. Okay, so these are the two cases. Either it will be cyclic group or it will be the following group, which will be generated by two elements x and y, such that x is an order P element and y is an order Q element, and they have this following relation where S satisfies this equation. Okay, so now let us try to prove this. So let us first consider the case when Q doesn't divide P. Okay, so before that, let us count how many silo P and silo Q subgroups will be there. There are only two divisors, prime divisors. One is P, another one is Q. So there will be a silo P subgroup and there will be a silo Q subgroup. Okay, so let NP denotes the number of silo P subgroups of G, and NQ denote the number of silo Q subgroup of G. Okay, so now according to third theorem, NP should divide Q and NP is congruent to 1 mod P, right? So from there, what value of NP are possible? So NP divides Q. Q is a prime number. So that means NP can be either 1 or it can be Q. Okay. 1 satisfies this second equation. Does Q satisfies this equation? Is it possible that Q satisfies this equation? What does it mean that Q satisfies this equation? That means Q minus 1 should be
no,
divisible by P. But I have assumed my Q to be strictly less than P. So Q minus 1 will be again strictly less than P. So it will never be divisible by P. Therefore, there will be only one choice for NP, that is equal to 1. Is this clear?
Yes.
Okay. Now, what will be the choices for NQ? Let us see. So NQ will divide P and NQ will be congruent to 1 mod Q. So the choices for NQ is either 1 or P. Right? So if Q divides P minus 1, which is one of the cases, then NQ can be equal to P, right? So for NQ, we will have two choices, either 1 or P. Is this fine? Should I go to the next page?
Yes, ma'am.
Okay. So now, by similar argument, NQ divides P and also NQ is congruent to 1 mod Q. This implies that NQ is 1 or P. Okay. Now I will break it into two cases. The first case says that suppose Q doesn't divide P minus 1. If Q doesn't divide P minus 1, then this case will not arise. Then NQ will be equal to 1 itself, right? If this, then NQ is equal to 1. Okay. Thus, there exists only one CeLO P subgroup and only one CeLO Q subgroup. So let P be a CeLO P subgroup. Okay. Let P be a CeLO P subgroup. Then what can I say about the structure of P? This P will be of, yeah, P is of prime order and a prime order group is always cyclic group. So it will be generated by some element X such that order of X is equal to P, and let Q be a CeLO Q subgroup. Then Q will also be generated by a single element, as it will also be a cyclic group. And what will be the intersection of P and Q? Identity, because it is a subgroup of both P and Q, but both of them are of prime order. So it has to be equal identity. And then what will be the cardinality of this PQ? It will be nothing but PQ. Yeah. And both P and Q are normal subgroups, right? Both P and Q are normal subgroups of group G. Therefore, what I can say, that G, which is equal to PQ, is isomorphic with P cross Q. That means this is isomorphic with Z quotient PZ cross Z quotient QZ. But what is this? P and Q are co-prime to each other. Therefore, this is isomorphic with Z quotient PQZ. Is this fine to everybody?
Yes, ma'am.
So in this case, we are getting that G is a cyclic group of order PQ. Okay. Now we will consider the other case where Q divides P minus 1, and we will try to see in this case what is happening. Should I go to the next page?
Yes, ma'am.
Okay. Case 2. Case 2 is suppose Q divides P minus 1. In that case, so now we are assuming that NQ is equal to P. Okay, that means there are P many silo Q subgroups. So there exist P many silo Q subgroups. Okay. So, but each silo Q subgroup will be generated by a single element. Okay. So, let P be a silo P subgroup such that P is generated by a single element X. So, it is having this many elements, and Q be a silo Q subgroup such that Q is generated by Y. So order of Y is equal to Q. Now P is normal subgroup of G, as P is the only one silo P subgroup. Therefore, P should be normal. Okay. So therefore, if I consider YX, Y inverse, then it should belongs to P. So from here, I can say that Yx, Y inverse will be equal to x to the power R for some R in between 1 to P minus 1. Correct? It's the same thing that we have done for this other case. Okay. Now, again, if I assume that R is equal to 1, then what will happening? In that case, I will get that Yx is equal to xy. Okay. And in that case, you can show that then G is abelian, and we get that G is isomorphic with the cyclic group, this one. But we don't want to go into that case. So that means we will assume that R is not equal to 1. So in that case, what will happen? So then I will get, so say Yx, Y inverse is equal to x to the power R. Okay, so from there I see that y square x y to the power minus 2 is x to the power R square. Sorry?
Previous slide.
Oh. So similarly, you can keep on doing these steps, and you can go up to y to the power q, and then you can see that this is nothing but give you one relation in terms of R. Okay.
Okay.
So similarly, we get that y to the power q x y to the power minus q is nothing but x to the power R to the power q. But this is nothing but x, as order of y is equal to q. So from here I can say x to the power R to the power q minus 1 is identity, which implies that P divides, because x is an order of x is equal to P, therefore P divides R to the power q minus 1. Okay. That means I am getting that r to the power q is congruent to 1 mod p. Therefore, G is isomorphic with the group which is generated by two elements x and y, such that order of x is equal to p, order of y is equal to q, and y inverse is equal to x to the power r, where r to the power q is congruent to 1 mod p. Okay. Is the proof clear to everybody? If you have any doubts or any questions, please ask. No? So before proceeding further, do you have any doubts in understanding the statement of Selous theorem? Any one of the Selous theorem? The statement is not clear to you? Then please let me know at this point, because now we will be heavily using these facts and it will be difficult for you to understand. So if you have any doubt or any difficulty in understanding the statements of the Selous theorem, then please let me know.
Ma'am, please could you repeat statement third once again?
Statement third. The third statement of the Selous theorem.
Yes, ma'am.
Okay. So the third statement was, yeah. So the third statement counts how many Silo P subgroups are possible in a group G. Okay. So it counts that how many Silo P subgroups will be there in a group G. Okay. So it says that this number, that the number of Silo P subgroup should be congruent to 1 mod P. That means this number minus 1 should be divisible by P, and the other one is that NP should divides M. So if you recall, what was your order of G? The order of G was P to the power alpha into M, such that P doesn't divides M. So this alpha was the highest possible power of P that was present in the order of the group. Then it says that this number of Silo P subgroups in P should divide the other factor, this M, and it should also simultaneously satisfies this equation. Okay. Is it fine?
Yes, ma'am.
Okay. Okay, so now we will see just one corollary to this uh, case that we have already proved just now. What is the corollary? So let P be an odd prime and G be a group of order 2p. Then it says that either G will be isomorphic with the cyclic group of order 2p, or G will be isomorphic with the dihedral group dp. Okay. So P is a prime, 2 is another prime. So it is just product of two primes. And we have already discussed the general case, that product of two primes P and Q. In that case, we have seen there are two choices, right? So here also I am specifying one of the prime number to be equal to 2. And then it says that in that case it will be either the cyclic group or the dihedral group, because this dihedral group we already know. Okay, so if you go through the proof, so there are two cases. One case will be if, so by previous proposition, if 2 doesn't divides p minus 1, in that case what we will get?
Isomorphic to Z to P.
Yeah, in that case it will be isomorphic to the cyclic group of order 2p. Okay, and the other case is if 2 divides p minus 1. Okay, then what do we have seen? Then G will be isomorphic to the group generated by X and Y.
Hello, ma'am.
Yes.
Hello, ma'am.
Yes.
Now, how it be possible to does not divide p minus 1? Because p is odd prime.
P is an odd prime, so it will always be divisible. So this case will never arise, right?
Yes, ma'am.
Yeah, you are saying, yeah, okay, fine. So maybe we don't have to consider, correct, you are correct. So this case will never arise. So we will be left with the case when G divides, correct, good. So we will be left with the case that, fine. So P always divides. So
we can write that as if let P be any prime, then these two are cases. Because for P is equals to 2, it will be Z4.
yes, that is a like that will be this just group of order 4. So that we already know, that is any group of order p square. How does this structure?
Yes, ma'am.
Okay. Yeah. So if so, I am assuming that 2 divides. So this will be always the case that 2 divides p minus 1. Okay. Then we know that G will be isomorphic with the group generated by two elements x and y, such that order of x is equal to p, order of y is equal to 2, and also I will be having y inverse is equal to x to the power r, where what will be the condition on r? What will be the condition on r?
RQ mod mod 2.
Yeah, r square should be congruence to 1 mod p, right? Okay. So r square is congruence to 1 mod p. What does that mean? That means that p divides r square minus 1. Correct? So r square minus 1 is r minus 1 into r plus 1. Okay. So that means there will be two cases. So if, because p is a prime number, so if p divides r minus 1, then what I will get? Then r will be congruence to 1 mod p. Okay. So in that case, what do we get? In this case, we will in fact get that y inverse will be equal to x, and from there you can conclude that G is abelian. Okay, therefore G will be isomorphic with the cyclic group of order PQ. Okay, is this fine?
2p.
Sorry, oh, 2p. Yeah, sorry. I have not written here all the details. There are few things left behind, but you can fill in those gaps with the proper arguments. Okay. Fine. So G is isomorphic with Z2P in this case, and the other case is P divides R plus 1. If P divides R plus 1, in that case, what does it imply? R is congruous to minus 1 mod P, right? So in that case, what will happen? In that case, I will get that Yx Y inverse should be equal to X inverse. Okay. Therefore, in this case, G will be the group generated by X and Y such that order of X is equal to P, order of Y is equal to 2, and Yx Y inverse is equal to X inverse. This is nothing but the dihedral group, because this is the relation of the dihedral group. Is this fine?
Yes, ma'am.
Okay. So this gives you the characterization for a group of order PQ. So similarly, there are so many cases that you can try by yourself. And next thing that I would like to do is classification of the group of order 12, which is a non-trivial thing. And here you will see that there can be many possibilities of a group of order 12. Okay, so next thing is classify group of order 12. Okay, so if we would like to classify group of order 12, then first of all we need to do the prime factorization of 12. So 12 is nothing but 2 square into 3. So what are the possibilities for CELO subgroups?
CELO 2 and CELO 3.
2 and 3. CELO 2 and CELO 3. What will be the order of a CELO 2 subgroup?
4.
4.
4. Because the highest possible power of 2 is 4. That means CELO 2 subgroup will be of order 4. Okay. So we will see now what are the possibilities. In fact, we will see that there are 5 different isomorphic classes. There are 5 different isomorphic classes. Order 12. So see, the 12 is not a very big number. 12 is a small number only, but still you can find 5 different groups of order 12. There can be 5 different structures are possible in just a group of order 12. So what are those? One will be, of course, the cyclic group of order 12. Cyclic group of order 12. Second is the A4. Do you know what is A4?
Yes, ma'am.
It's a group of S4.
Yes, group of even permutations of S4. Okay. So did I said the notation AN in general to denote the group of even permutation of SN?
Yes, ma'am.
Okay, then
Yes,
that is
ma'am.
fine. Okay, that's good. Okay, so these are the two different types. And then do you know any other group of order 12?
D6.
Z2 cross Z6.
D6, exactly. D6 already you have studied. So D6. So D6 first is the structure. It will be generated by two elements X and Y such that order of X is equal to 6, order of Y is equal to 2, and YX, Y inverse is equal to X inverse. So this is another example. And then there is another possibilities. This is Z quotient 2Z cross Z quotient 6Z. Okay. Is this an abelian group?
Yes, ma'am.
Yes.
Ma'am.
Because both of them individually are abelian group, right? Is this a cyclic group?
No, ma'am.
No,
No,
ma'am.
ma'am.
No, ma'am.
No. Both of them individually are cyclic group, but their product is not a cyclic group. Okay. When the product of two cyclic group will be cyclic?
If they are
GCD1.
co-prime.
GCD.
If their GCD of
Is
these two numbers are co-prime in that case. Okay, good. Now the fifth option is that G will be generated by X and Y such that order of X is equal to 4, order of Y is equal to 3, and I have the relation that XY equal to Y square X. Okay. So these are the 5 possibilities. So you can see that 12 is such a small number, but still you have 5 different groups of order 12. Okay. So now let us see how do we get all these 5 different groups. So the classification of group is not an easy problem. So you give any arbitrary number n, and if you ask that what are the possible different groups are possible of that order, then it is not an easy task to do. Okay, sometimes if these numbers are of particular form, then you can conclude, but in general it is not so easy. Okay, especially if when you will have more and more factors of that number, then you will get more and more complications. Okay, so we have seen that there are two prime factors, one is 2, another one is 3. So there will be a possibility of a CELO 2 subgroup and a possibility of CELO 3 subgroup. So N3 denotes the number of CELO 3 subgroup. Then what do we know? That N3 should divide 4 and N3 is congruent to 1 mod 3. Then what are the possibilities for N3?
1 or 4.
1 or 4. There are 3 divisors of 4, 1, 2 and 4, but 2 doesn't satisfy this equation. Only 1 and 4 satisfies this equation. So the possibilities for N3 is 1 and 4. Similarly, N2 is the number of CELO 2 subgroup. So N2 divides 3 and also N2 is congruent to 1 mod 2. What are the possibilities for N2 now?
1, 3.
1 and 3. These are the two divisors of 3 and both satisfies this equation. Therefore, there are two possibilities for N2. Either it will be 1 or it will be 3. Okay. So now let us start with the Should I go to the next page?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So now let H be a silo 2 subgroup. If H is a silo 2 subgroups, then what will be the order of H? It is 4. Correct? Then what can I say about H? What will be the structure of H?
Either abelian or cyclic.
Either abelian or cyclic. That means it will be either Z quotient 4Z or it will be Z quotient 2Z cross Z quotient 2Z. Because any group of order p square, we have already seen either it is isomorphic with the cyclic group of order p square or it will be isomorphic with Z quotient pz cross Z quotient pz. Right? So this is the cyclic group. And this is known already. This is V4, known as the Klein 4 group. Okay, so now H can have two possibilities. So far, whenever we were dealing with silo 2 subgroups, silo 3 subgroups, or other silo subgroups, we have seen that on all the cases so far, it was a group of prime order and therefore it was always a cyclic group. This is the first time we are encountering a case where it is a power of a prime number. So it is not only just the possibility group, there is another possibility which is the abelian group. Z2 cross Z2. Okay, so be very careful while dealing with this because most of the time whenever it comes, people are so used to of having that silo p subgroups will be a cyclic group, so they just write down it will be a cyclic group. So be careful at this stage. Okay, and let K be a silo 3 subgroup. Then order of K is equal to 3. And what will be the structure of K?
Isomorphic to Z3.
Cyclic.
Yeah, this will be cyclic group because 3 is a prime number. There is no other choice. Okay. So then we are getting this. And what about H intersection K?
Identity.
Identity. And so I will be having that order of HK is nothing but 12. So this implies that G is equal to HK. Okay, fine. Now the first observation that, so I am saying that there are two choices for number of silo 3 subgroups and there are two choices for number of silo 2 subgroups. Okay. Now my first claim which I am putting as a lemma says that either H or K is a normal subgroup. Of G. I'm saying that one of them has to be a normal subgroup of G. What does that imply? In number, in the count of silo 2 and silo 3 subgroups?
Unique.
If H is normal, then the number of silo
Yeah.
H 1.
Yeah. So that means simultaneously I cannot have 3 silo 2 subgroups and 4 silo 3 subgroups. Okay. One of them has to be equal to 1. It says this. Okay. So let us see why. So let K be a CeLO3 subgroup which is not normal. What does it imply? That imply that number of CeLO3 subgroups will be equal to 4. Because if it is 1, then it would have been normal. But since I am assuming that it is not normal, that means the number of CeLO3 subgroups is not equal to 1. Therefore, it has to be equal to 4. Okay. So if number of CeLO3 subgroup is equal to 4, then in one CeLO3 subgroups, how many elements are there of order 3?
2 elements.
2.
2 elements apart from identity. There are 2 elements of order 3. Okay. Now let K1 and K2 are 2 CeLO3 subgroups. Okay. What can I say about their intersection? How many elements will be there in the identity?
Identity.
Because yeah, K1 and K2 I am
Otherwise, it
choosing
will
to
yes.
be 2. Yeah, I am choosing it to be 2 different CeLO3 subgroups. Okay, so K1 intersection K2 will be a subgroup of K1 as well as K2, but both of them are of order 3 and both of them are distinct. Therefore, K1 intersection K2 should be equal to identity. What does that mean? That means if you take any 2 CeLO3 subgroups, then they intersect trivially. Okay. So now from there, can you calculate how many order 3 elements is possible in this group G?
8.
8. Because in each CeLO3 subgroup, there are 2 elements of order 8 and there are 4 CeLO3 subgroups and they intersect trivially. Therefore, there will be total 8 number of elements of order 3. Correct? So if there is total 8 number of elements of order 3, then how many elements are left?
Apart from identity 3.
3.
Apart from identity 3, so if I include identity, then there are 4 elements left, right? So if there are 4 elements left, then what will be the choice for H, a CeLO2 subgroup? How many are possible?
1.
Only one.
Only one.
That means it forces me that there will exist only one CeLO2 subgroup. Is the argument clear to everybody?
Yes, ma'am.
Okay. So it says that, now let me write down what I have just said. Any 2 CeLO3 subgroups intersect trivially. Therefore, number of elements of order 3 in all in G is equal to 8. Hence, there is only one CeLO2 subgroup in G. Therefore, H is a normal. So that means if I am starting with K to be not normal, then it forcing my H to be normal. That means that one of them has to be equal to normal. Okay. So we have proved that either H or K, one of them has to be always a normal subgroup. Okay, fine. Now I will divide it into different cases, and then I will try to show that we will be getting these 5 choices. Okay, so before proceeding, so maybe we will take just 10 minutes break here, and then we will come back and complete the proof. Okay, so we will again meet at 10:07. Okay. Any doubt so far? Okay, then we will meet at 10:07.